Hello and welcome to the Logic Minute. In this video, we will discuss the operation of the output structure for standard CMOS devices. Almost all logic devices have a similar internal structure, with ESD protection, input buffers, an internal logic function, and an output driver. In this video, we're going to look specifically at the output driver section. There are many variations of circuits used as outputs for CMOS devices. However, the most common is the very simple CMOS inverter. Vin indicates the control voltage coming from the internal logic function, and Vout indicates the output voltage of the device. The MOSFETs in the output structure are voltage controlled, and their control voltages are defined as VSG and VGS. Since the input to this inverter is controlled by the internal logic of the device, the input voltage can only be either 0 volts or the supply voltage. This means that only one output MOSFET can be on at a time. Also, it means that when either device is on, the control voltage is always equal to VCC, which greatly simplifies our analysis. For the PFET, VSD is VCC minus Vout, and for the NFET, VDS is just Vout. Since only one MOSFET can be on at a time, let's look at the case where the PFET is off and the NFET is on. This is what we would call the low output state, and in this condition the device will sink current from the output to ground. Sweeping the output voltage, the current into the device would look something like this. Output voltages lower than this line will result in the device being biased into the ohmic region, while voltages higher than this line will put the device into the saturation region. In the saturation region, the MOSFET will act much like a constant current source, only increasing current slightly as the voltage is continually increased. Most of the time, a logic device will not be operating in the saturation region because that region starts one threshold below the supply voltage. Typically, with an output in the low state, we expect the output voltage to be very close to 0. Looking closely at the voltage-current relationship, we can see that the slope is nearly linear when the output voltage is relatively low. Because of this, the output MOSFET can be modeled as a resistor for normal operation. From the datasheet, we can estimate the worst-case output resistance of a device for a given set of conditions. All we need are the output voltage and current values. For an example, I will select a supply of 4.5 volts. The measured maximum output voltage of 0.3 volts is provided for the test condition of 6 milliamps. With those two values and Ohm's law, the maximum output resistance is calculated to be 50 ohms. It's important to note that this is the maximum value across process variations and temperature. This whole time we've only been looking at the case where the PFET is off and the NFET is on. Almost everything I've shown holds true for the opposite case as well. The most important factor to note for the output high state is that the source-to-drain voltage for the PFET is VCC minus the output voltage. So one extra step is required to calculate the output resistance of the PFET. Thanks for watching. If you have any questions, please come on over to the E2E forums where you can ask us directly.